So far, we have spent about 9 lectures discussing conduction, convection and radiation. Now, for the remaining 3 lectures that we want to spend on the application of heat transfer fundamentals to metals and materials processing. So, we want to see the relevance of the subject that you have learned so far. Several examples I would like to elucidate in the next 3 lectures, because I have given you the handout and you have seen that we will have about 5 problems. There are 16 lectures. I think 3 lectures on application, 9 or 10 lectures on the theory portion, and remaining 5 or 6 lectures on problem solving. So, the next 3 lectures we will address, and this is therefore application lecture 1. And as I said, that every stage heat transfer is important in metals and materials processing, particularly because I am a metallurgist. So, I will talk with regard to metals processing, and because during the extraction of molten material, extraction of metals, we go through a phase of molten metal, and then converting the molten metal into a solidified product before we supply the material to the customer. So, there is heat which is pumped into material and heat which is taken out. In the final stages, heat is taken out, so that the material comes to the room temperature and can be supplied to the customer. On the other hand, during the processing itself, in order to have better kinetics, we want to carry out process at high temperature, and often we encounter liquid metals, as in blast furnace, as in copper converter, as in steel making, and so on and so forth. So, there is a good number of examples. I will start with the most simple one, and I intend to demonstrate in the next 3 lectures several problems, and starting today with the furnace heating and cooling operation. This is very important. Then we can say furnace cooling versus air cooling. Little bit of discussion could be made. If I do not have enough time, furnace versus, this will be done in the next lecture. Then we have alloying, where we project solid material into a liquid material and then make alloys, maybe copper silicon alloys, or maybe aluminum silicon alloys, or niobium iron steel alloying, and so on and so forth. So, this essentially alloying essentially implies that we will add a solid material into a liquid, and whereby the solid material will melt and disperse, giving a homogeneous material having different composition than the parent one. We can also have some furnace lining examples, where we want to use refractory materials and insulating materials in order to contain heat, because we are talking about metals extraction at very high temperature, and we must understand that we are talking about the radiation becomes extremely important in our context, that you must remember, because the surface temperature that we are talking about are often whether it is even a solidified. If you can imagine a product coming out of continuous casting mill, the slab has a surface temperature of about 1100 degree 1000 to 1100 degree centigrade, and in that case you can imagine raised to the power 4, therefore should be the value of it. So, and furnaces also are maintained at very high temperature, 1000 degrees, 1200 degrees, 1400 degrees sometimes. So, the furnaces needs to be lined with insulating material, high grade insulating and refractory materials. So, some examples we will discuss about how to reline the furnaces, or how industrial furnaces are relined, and we will also talk about. So, this is basically melting and dissolution. The dissolution part is mass transfer, that will be done later on, but it is basically the melting part that is going to be discussed in this particular case. So, furnace lining examples will also be given, and then we will talk about maybe some contact thermal resistance. These are all we have learned already, thermal resistance. For example, we have in continuous casting mold, the first exercise that I have done when I initiated the discussion on fluid flow. If you remember, I considered a film flow, and that film was essentially refractory material, which are powder material, which are oxide material, which part of it is liquid, part of it is solid. And there what happens is, between the descending strand and the mold surface, the film exists, and the film offers resistance, and there is a film to strand and film to mold contact resistances. And we will also see that our fundamental knowledge will allow us to determine the contact thermal resistances, maybe between a solid and a liquid, okay, as it is in the case of a ladle shroud, for example, through which molten metal flows, and the molten metal does not necessarily completely wet the shroud or the refractory surface, because they often contain graphites and so on and so forth. So there is a finite contact thermal resistance. How such thermal resistances can be calculated, that also will be demonstrated. So a number of exercises that examples that will be taken up right from now onwards during the next 2 lectures, whereby we will tell you that what are the applications of potential applications of the theory that we have learned. In the case of furnace heating and cooling operations, this basically there is no liquid phase involved. This is basically a solid state processing operation, solid state processing operation. So we are fortunate that we do not have to address here basically fluid flow, but we must understand that if you talk of furnace heating operation, suppose if you take the furnace, why is furnace heating important? Heating in a furnace, because we want to carry out most of the cases, we want to produce different kinds of products, maybe coil, maybe slab, maybe bloom, okay, and every time we may not produce those products directly by solidification of molten metal. Some mechanical working needs to be done, and we all know that we want to do mechanical working at above recrystallization temperature, because at that stage deforming the molten material, deforming the solid material becomes very easy. So basically, before thermomechanical treatment, solid ingots, slabs, etc. are routinely reheated in furnaces. These furnaces could be either gas fired furnaces or liquid fuel fired furnaces, liquid fuel. So we can introduce blast furnace gas, combust the blast furnace gas with oxygen, and that is how heat is going to be liberated. That, so there may be burners here, or there may be, you can be introducing some liquid fuel, okay, petroleum or similar kind of furnace oil, for example, and then they can be mixed, atomized with oxygen, they can burn in the furnace and then produce the heat itself. So within the furnace, this is a different subject, there is extensive amount of fluid dynamics. So there is a combustion mechanism which is involved here, combustion phenomena is involved at the burner, and there is combined convection, conduction, radiation taking place. But consider the solid. If you consider the solid, within the solid, the heat transfer is solely by conduction, that we all know, and our domain of interest is basically the solid, and we are assuming that the furnace temperature is remained constant. So the ambient temperature is constant. Typically what happens, the furnace which if you maintain at how it is maintained, suppose you start firing the furnace by injecting gaseous fuel or liquid fuel into the furnace. These are my schematically shown burners, okay. So once you start doing that, after some time what happens, the furnace attains a constant temperature, and once the furnace attains a constant temperature, it is the time or the desirable temperature, which may be 1200 degrees centigrade for steel industries, for example. It is at that time you put in the solid objects into the furnace. So typically if you look at the furnace temperature happens something like this. So this is initially the furnace is cold, and then after, with combustion taking place, the furnace attains your desired temperature, okay. That may be, as I said, could be about 1200 degrees centigrade. So this is furnace temperature, and this is time. The moment you put in 1, 2 or 3 ingots, the furnace, what happens is the temperature dips down, but at that point what happens, you increase the pumping rate of the fuel, and soon enough the desired temperature is obtained. So, more or less we can say that by adjusting the flow rate of the fuels into the furnace, we should be able to maintain a constant temperature, and the task in furnace heating and cooling operation, that we will heat it, and then once it attains, it can attain the maximum temperature as this, when there will be thermal equilibrium. So, initially when I put in the solid into the furnace, then what happens, the solid is at room temperature, but after some time what happens, the solid attains thermal equilibrium, and if I take out the ingot again from the furnace, so from 1200 degrees centigrade the temperature of the solid object is going to go. So, if I now for example draw the solid objects, the solid object will look, temperature profile will look something like this schematically. So, this is the time when the equilibrium has been reached, that means I can say that the solid has reached the furnace temperature. So, this is furnace, this is solid, and this is the heating operation, H for heating. Now, similarly if you look at the cooling operation, so we have gotten to this temperature, so the 1200 degrees centigrade. So, the furnace, so we have from 1200 degrees centigrade, then what happens is I will draw it like this is better, so that you are not confused, and this is my ambient temperature, which is 25 degrees centigrade, and this is time, and this is the cooling operation. That is how typically I know these are not going to change linearly, and also what is this temperature? This temperature could be the average temperature, because the inside temperature and surface temperature are not going to be identical. When you heat, the surface temperature is going to increase at a much faster rate, but the interior is going to increase at a much slower rate, because there is a substantial amount of thermal resistance between the center and the surface. The converse is going to take place, the surface is going to cool much faster rate, because it is exposed to the environment from all sides, but the interior is going to be cooled at a much lower rate. So, this temperature which I have represented here essentially is an volumetric average temperature that I have represented the ingots or the solids temperature in the furnace. So, in the analysis what we are going to consider, that the surrounding temperature, whether we are talking of furnace heating or furnace cooling operation, the surrounding temperature or the ambient temperature can be taken to be constant for all practical purposes, and this sort of a dip which typically is encountered in the industry, but rapidly compensated by pumping additional amount of fuel, okay, we can neglect such variations, and for all practical purposes we can. The process, understanding of the process is very important, and then only you can write the equations, then you can solve the equations, and then you can get some idea. What could be the objective here? The objective here could be, I would like to know that using my heat transfer fundamentals, whether it is possible to tell me that this ingot which I have introduced into the furnace at 10 o'clock, at what time the ingot will attain a homogeneous temperature which will be in thermal equilibrium with the furnace temperature itself. So that I know that, well, by doing calculations, by solving the differential equations, I can find out that yes, you have put in this ingot which is at 25 degrees centigrade at 10 o'clock, at 12:35 hours, what happens is this ingot will be completely in equilibrium with the furnace temperature. So that I do not do any arbitration. If I go to 4 o'clock also, 4 o'clock only also there will be equilibrium, but by the time I have lost quite a bit of time. So, pinpointing the time at which the homogenized temperature is obtained is very, very important for us. Similarly, here also we would like to know that at what time the center of the ingot attains the room temperature itself. That may be a parameter of interest, or what is the rate of cooling, at which rate it is cooling, and if I want to increase the rate of cooling, what I should be doing. Okay, and all those informations are basically needs to be worked out when we desire to be worked out when we talk of furnace heating as well as cooling operation. As I said, this you can understand, or you can put these operations in terms of heat transfer mathematical equations and so on and so forth, provided your understanding of the process is very clear or not. So, if you look at furnace heating operation, therefore, I would say that the characteristics of furnace heating operation is number one, we understand furnace temperature is constant. Solid's initial temperature is known. Because this solid may be in this yard for some days. Okay. So, the initial temperature filled may be the room temperature. If you say no sir, I have gotten this solid right now from another furnace or from the continuous casting machine or from the ingot mold, then I will say that I have told this point earlier also, that the initial temperature within the solid must be, initial condition must be known. If the initial condition is not known, in that case we will not be able to solve or work out the implications of the equations that dictate the heat transfer processes. So, this is now the third thing is, we can say, well, the temperature changes. So, we have to know the thermophysical properties, density, specific heat, thermal conductivity, etc., and mind it that I am not interested to find out the temperature profile within the furnace itself, etc., or the burning rate of the fuel. My job interest is this particular domain, which is, and if there are multiple ingots, I have to work out the radiation view factors also, as you all know. Now, this ingot, we must understand that this is going to be, there is going to be huge difference between this temperature. So, this is going to be basically the heat is going to be transferred from the furnace to the solid, okay, by mostly by the mechanism of radiation, because of the simple fact, as I have indicated earlier, that the temperature. Okay. Now, between the convection flux, if there is a convection there, then I can say that is the rate at which heat is being transferred, the heat transfer coefficient times the ambient temperature, which is constant, but the surface temperature is changing as a function of time. So, therefore, this is going to be the rate at which heat will be coming into the through the surfaces, but this rate is going to be substantially smaller than the corresponding rate, which is sigma into, I can say this is heat flux I have represented. So, I can say theta a to the power 4 minus theta s to the power, the corresponding heat flux, this Q convection and Q radiation. So, the heat, this, because it is high temperature, the furnace temperature could be 1200 degrees centigrade. So, this flux is going to be substantially higher than the convection flux itself. You can also consider that heating is by, if you are very fussy and you want to consider everything, heating is by a combined mechanism. Of convection plus radiation. Note that within the solid, heat flows by conduction only, and we have learned the theory of conduction very well, quite extensively earlier. So, we can say within solid, heat flows by conduction. So, you can say this is surface heating, I would write surface heating. So, energy exchange between the two objects at the surface. So, that basically determines, that will determine, as I formulate the process, the boundary conditions to the problem, because this represents the line of demarcation between, we isolate the surroundings from the system itself. The heat transfer, it takes place by conduction, and we understand that it is unsteady because the temperature is changing as a function of time. The heat transfer is essentially, so it is a conduction heat transfer, it is an unsteady heat transfer. Now, you can make simplifications depending on whether it is an infinite cylinder, 2-dimensional, 3-dimensional. Most of the industrial objects are 3-dimensional, so I could say heat transfer is 3-dimensional. I can also say that K rho Cp are known. This you have to have equation of state in order to understand that how the varies as temperature and so on and so forth. If you are not so fussy, you can work out on the basis of a constant thermal conductivity, specific heat, which are representative of the film temperature. So, film temperature we have solved in one example, as you know earlier, that it can be taken that if you know the TA, okay, and if you know the initial temperature 25 degrees centigrade and TA. So, you take an average temperature and that on that average temperature you can evaluate this, and this will depend on whether it is a steel sample, whether it is a copper sample or there is a aluminum sample and so on and so forth. So, therefore, when you put a solid object within the furnace, the temperature within the solid will change, and that if T represents the temperature of the solid, it is going to be a function, and if you are using a Cartesian coordinate system to represent the solid object, okay, I can say that we can understand that the temperature is going to be a function of time, x coordinate, y coordinate and z coordinate. Of course, the span of the x, y, z coordinate to be known to us, that means the dimensions of the solid object has to be given to us, we know the dimensions. Or we can say that is not the right way to write, dimensions, solid dimensions are known. So, the domain of interest is known. Solid dimensions are known means the domain of interest is known. So, the moment I have said that heat flows by conduction, so therefore, we will use Laplace type equations, basically conduction equations, and that we have to write down an unsteady state conduction. So, we can now look at the 3-dimensional phenomena, unsteady state conduction. So, therefore, I can say clearly that look, the equation will look something like this, we have studied earlier. This equation you have seen earlier, unsteady state term, conduction along the x direction. This, while the minus of this term essentially represents the conduction heat flux along the x direction, minus of this term, bracketed term, essentially represents conduction flux along the y direction, minus of this term within the parenthesis represents the conduction flux along the z direction. This we have seen, and this part we have solved very extensively. We have given you the summation solution in the context of a slab geometry. We have given you the error function solution. Now is only that we are not talking of 1-dimensional parameter phenomena, but we are talking of 2-dimensional or 3-dimensional heat conduction. I have introduced a term here S, which represents the heat source term, and when you heat a solid sample, there could be phase changes within the solid. Okay? For example, in steel you can have, when you are heating, you can get perlite transformed into austenite. Okay? And those reactions can have, they may have a very small value in terms of the overall temperature of the process, but nonetheless, if you want to consider, then you will find out that this S is a very finite, has a finite value, and that S, an expression of S could be something like rho delta H, where gamma S represents the fraction of the solid changing as a function of time. So, how much perlite has changed into austenite, the rate of change of the phase under consideration, that is what it is. This is the heat of transformation. So, this is kg per meter cube density, this is joules per kg. So, this becomes joules per meter cube. So, therefore, this is dimensionless volume fraction joules per meter cube per second, and that is what is each term, okay, watt per meter cube, that is the dimension of each of these terms, and S will also become. And what does this S represents? This represents the rate at which perlite is changing into austenite, and that change is associated with a heat effect which is delta H, and therefore, the volumetric rate, this S is called the volumetric rate of heat generation within the scene. To evaluate this, we have to take care of a continuous cooling diagram or equilibrium diagram, depending on the kind of assumptions one can make, because this S term this is dependent on temperature, as you can see here, because the phase change, how much of perlite will be changing to austenite, that will depend on what is the state of temperature. If the temperature is 200 degrees centigrade, there is no change. 200 to 25 degrees centigrade, 2050 degrees centigrade, all the perlite will remain as perlite, nothing is going to change. So, in that time this is going to be 0. So, this term, whatever I have shown here encircled here, is going to be dependent on the temperature itself, but we intend to calculate the temperature. So, therefore, this brings in non-linearity into the system. This is not known. So, this is to be calculated as a part of the solution. So, you cannot solve this equation. The point I want to make here is that you cannot solve these equations by analytical means, error function solution or infinite summation series will not apply. You will have to resort to numerical methods in order to solve this particular equation, but solution is not what we are talking about. We must understand that in addition to this source term, we will require one boundary initial condition here, 2 here, and I have outlined in detail earlier, okay, how to derive the number of the boundary conditions. Second order, so along x 2 conditions, second order y 2 here, so altogether 7 conditions are going to be needed. Initial condition is already given, because the initial condition at point 2, as I said, is already known to us. So, therefore, these boundary conditions are given, okay, initial condition is known to us. What are the boundary conditions? As I have indicated, through surfaces, okay, as you can see here, the ingot may be resting on the floor. So, the floor is exposed to a different kind of a boundary condition. If it is staying on refractory, we can assume that there is not much heat exchange between the two, or if there is a refractory at high temperature, there could be a contact thermal resistance that could be taken. But this surface, this surface, this surface, so if it is a 3-dimensional object, there are 6 surfaces, one surface is touching the bottom of the furnace, okay, but the remaining 5 surfaces are exposed to the environment, and through the remaining 5 surfaces, okay, we will have boundary conditions. So, expressed in terms of heat flux, that we can say sigma theta S theta furnace to the power 4 minus theta surface to the power 4. That essentially represents the flux boundary conditions. So, furnace temperature raised to the power 4 minus surface temperature, and this surface temperature is changing as a function of time, because T is, or theta is a function of T, x, y and z. So, therefore, this is position dependent, this is temperature dependent, this furnace temperature is constant. So, the flux values, flux boundary condition can be applied here, and as I said, if you want, if you are fussy, as I have indicated that here heating is by a combined mechanism of convection and radiation. So, therefore, you can say that heat is coming from the furnace to the solid not only by radiation, but also by convection, and then you can add to it that what is H into theta furnace minus theta A. So, the net flux, therefore, I would say, I will remove here. So, I will say this is the combined convection radiation flux prevalent at the surfaces. So, this is equal to theta S minus, sorry, theta furnace minus theta A. All the 5 surfaces of the solid are going to be heated by, according to this particular expression. Okay. On the other hand, the 6th surface is going to be heated in terms of, you can take that, if there is a perfect contact between the refractory, you can say this surface temperature is going to be equal to the refractory temperature, which may be equal to the furnace temperature. Or if you want to do it more exactly, then you can take into account a contact thermal resistance between the two, okay, in terms of a resistance, because you know that what is the furnace or bottom surface temperature, which is 1200 degree centigrade. So, if you add that contact thermal resistance like a inverse of heat transfer coefficient, so you should be able to find out that what is the heat flux in this particular through this particular surface. So, this two surfaces plus one surface here, or on these 5 surfaces you can put in these boundary conditions, and on the 5, so 2 here and 1 here, on the 5 surfaces this boundary condition, combined convection radiation boundary condition will apply. On the other hand, on the 6th boundary condition, a different procedure will, or different formulation will apply, as I have indicated. Either a constant surface temperature you can take, which is simple, very simple, or you can accommodate also the surface contact thermal resistance into the derivation or into in a calculation scheme, and you have to know that what is the surface resistance, interfacial contact resistance between the two surfaces. One is the ingot, the other is the refractory surfaces. So, the governing equation can be formulated on the basis of the physics of the problem. It is a conduction heat transfer. We can identify based on our knowledge that how many initial and boundary conditions are to be needed. We also know that how to write these boundary conditions. For example, I can say that one boundary condition could be written at x is equal to 0 for y is equal to a and z is equal to b. That is the way we write the boundary conditions, right. I have shown, and you can say that the flux boundary condition essentially implies that this is sigma theta s to the power 4 and theta furnace to the power 4 and theta surface to the power 4 plus h and theta furnace minus theta surface. It is understood that the heat transfer coefficient is to be given to us. It is understood that theta furnace is to be given to us. We must understand that this equation essentially is one equation, one unknown, that unknown being T. So, rest all other parameters must be known. The S is to be known to us, it is to be calculated iteratively because it is a function of temperature, rho, Cp, K, thermal conductivity, etc. to be given to us, okay, in terms of their constitutive relationships. So, in that such that this equation boils down to one equation and one unknown. If you have one equation, one unknown, right number of initial and boundary conditions, that means we should be able to solve this expression, and once we solve this expression, okay, we should be able to generate these curves, okay, and we can say that look, this is the average temperature. On the other hand, this could be the surface temperature, this could be the surface temperature, and this could be the center temperature. This is the center temperature, center, and this is the surface temperature, because I have the slope of the lines are different. The surface is heating at a much faster rate because the surface is exposed to the high temperature environment. On the other hand, the center is heating at a, but nonetheless, as I have indicated that the surface could be attaining thermal equilibrium a little early. On the other hand, this could be attaining a thermal equilibrium little later. So, this essentially represents the average temperature as I have indicated in about a few minutes back. So, once we write down the equation, write down the boundary conditions, solve the equations through a numerical procedure, we should be able to generate these curves, and therefore, we will be able to find out that at what time, critical time, there is a thermal equilibrium between the ingot and the furnace, and that tells us that the ingot has reached a homogenization temperature at this particular point itself. But as I said that it is not possible for you to work it out because this equation defies any analytical solution. So, we will not get error function chart or an infinite series in order to work out the implications of that. Now, once homogenization has taken place, we bring out the object, still everything applies. What has now changed? That it is the same equation that applies, but the boundary condition has now changed. The boundary condition could now be the cooling problem is cooling and heating problems are basically analogous problems. Only essential difference is that in the heating cycle we have a heat flux which is coming from the furnace into the solid. On the other hand, in the case of cooling operation, what happens from the ingot surface, heat is being lost to the surroundings, okay? And that is what is a reverse kind of a profile that we are going to get in the case of this. Now, we are going to see that, well, if we write down, so the same equation will apply. There is going to be now perlite changing, austenite changing into perlite, because from the high temperature you have formed everything now austenite, and now you cool it down. So, austenite is going to be transferring into perlite. So, there is going to be the source, heat source term here. So, whatever is the value of the heat source term, that heat source term will appear here as a with a negative sign, okay? In the case of if you consider that it is positive during perlite to austenite during the heating, so it is going to be negative when you go from austenite to perlite during the cooling itself. So, the same heat source term applies. So, the equation does not change, the equation remains same, the source term, formulation of the source term remains same, okay? Only thing changes is the boundary condition to the problem, that will demarcate that what is the heating problem vis-a-vis what is a cooling problem. And if you consider a cooling problem, in that cooling problem you can say that the heat flux, that is going to be sigma. Now, surface is at higher temperature, ambient is at lower temperature. So, this is our cooling. Initial condition is known because I have taken it out from the furnace and we had temperature everywhere within the solid known, which is the temperature arrived at the critical time. So, it has become equal to 1200 degree centigrade. So, the cooling operation starts. What is the end solution of the heating operation becomes the initial solution for the cooling operation. I have taken it out, and now the cooling starts, and cooling starts because of this flux being operational, that there is a convection flux also, theta solid minus theta A. Cooling and heating are one and the same problem, they are fundamentally just opposite. So, the boundary condition will change, same equation with the changed boundary conditions can now be solved in order to generate this particular graph. And similarly, I can say that the surface is going to be cooling. If you work out the implication of the equations with regard to the boundary conditions, you must understand one point I want to make, that when initially, okay, when we have temperature difference is very, very large, okay, in that case what happens is that the radiation is going to be predominant. On the other hand, when you have temperature differences very small, it is going to be other way around. So, for example, at this particular case, when you just bring out the furnace, bring out the solid from the furnace, there is a huge difference. So, this term is going to be dominant over this particular term. But as the temperature changes, and when you come here, the radiation may not be, because at 60 degree centigrade, 70 degree centigrade, the radiation fluxes are not going to be that high. So, when the temperature difference between the ambient and the solid surface is changing, it is under that condition this can change. So, there are two extremities. Initially radiation predominates, towards the final stages convection predominates, in between you have a combined convection and radiation fluxes. But I would say, if you consider up to this particular time, the temperature is so high, 200, 300 degrees, even surface temperature will make the component contribution of radiation significantly high even in the cooling process. So, we can say that we can have different graphs here. So, we can have one line like this, which is cooling at a very faster rate, and the other line could be this, and you should be able to now tell me that which line corresponds to where, and this line therefore, which is cooling at a slower rate, this could be the center of the slab or the ingot, this could be the surface which is cooling, and this could be our average temperature that I have already explained to you. This essentially tells that the surface attains thermal equilibrium with steady state with respect to the furnace. The object has not attained thermal equilibrium, but steady state with respect to, because the temperature is not changing as a function of time, and that is what I am saying, that it is steady state. Okay? It is constant, which is equal to 25 degrees centigrade quite rapidly. On the other hand, the inside of the object is changing at a much slower rate and attaining the ambient temperature at a substantially longer time. So, we can calculate. So, this if you, for example, I have discussed this heating and cooling operation. So, the cooling need not be discussed in any further detail, because it is the same thing. Okay. So, it becomes boring to talk about the same thing again and again. Same equation applies by changing only the boundary condition. For example, I will discuss in the next class the furnace cooling operation, and that furnace cooling operation means essentially that after the ingot has attained a steady state temperature, now you do not want to cool it in the furnace. Okay. Cool it, bring it outside. You do not want to bring it outside and cool it in the ambient. You want to keep it inside the furnace, shut off the furnace, and then let it cool down. You know the operations, annealing versus normalizing. Normalizing operation essentially means air cooling operation. So, you want to take out the ingot after homogenization, and that is what we have discussed today. And tomorrow in the next lecture we are going to talk about the furnace. We are still concerned about the temperature within the solid, but now the furnace temperature will be changing as a function of time. So, this boundary conditions, this will also be a function of time, this will be a function of time anyway, because the solid's temperature is going to be changing, but this is to be given to us, that how theta furnace varies as a function of time, that information is to be applied in order to solve the furnace cooling operation. The history of the change in furnace temperature has to be given to us in order to simulate the furnace cooling. So, that furnace cooling, air cooling issue we will talk about in the next lecture. So, I think as far as heating and cooling operation of solids in furnaces are concerned, a fair bit of knowledge has been given, which tells us that the combined convection, radiation, and of course, if you have multiple ingots in the furnace, you will invoke the radiation view factor, you will use emissivity, you will use the radiation rate laws, you will use the conduction equations. So, all these fundamentals that you have gained or studied in the context of heat conduction, convection and radiations are applicable if you want to simulate or if you want to study an industrial process such as heating of an object in a furnace or cooling of an object outside the furnace itself. So, we will finish the lecture here, and I think we will continue in the next class with, as I said, that furnace cooling versus air cooling operation, what are the basic distinctions between the two, we will discuss elaborately.